For this circuit, it is said that at t is equal to 0, the switch moves from this position to this position. So we need to find the expression of current I through the capacitor here, which is of 2 farad. So we have to first find what is the voltage stored in the capacitor before t0, or when the switch is turned to this position, changed to this position. So we will draw the circuit again. Here this is 30 volts, and we can ignore the other source for the time being. So this becomes the circuit before t is equal to 0. So this is 2 farad here, this is 6 ohms, 3 ohms, 30 volts. So the voltage that is here, V, that will be the voltage stored across the capacitor, and we can find that voltage using voltage divider rule. So that will be 30 divided by 6 plus 3 times 3, which is 10 volts. So V0 is 10 volts, so we can write V0 here, which is 10 volts, which is the voltage stored at the capacitor. Now when the switch is in this position, we can redraw the circuit. Now we can ignore the other voltage source, which is the 30 volts voltage source. This is the new circuit now, and this is the capacitor, which is of 2 farad, and it has now a stored voltage of what, 10 volts, and 6 ohms here, 3 ohms here, and 12 volts. So we need to find what is the we need to find the current, but in order to find the current, we need to find the voltage expression across the capacitor. So for this situation, there is a source present, so we can use the formula. We have two formulas. One is initial value of the voltage plus Vi minus Vf e to the power minus t over Rc. We can use this formula. If we use this formula, we have to find what is the initial value. The initial value is 10 volts, which is given. We need to find the final value as well. Sorry, this one is final value. So Vf plus Vi minus Vf e to the power minus t over Rc. We need to use that formula. So V final value we need to find out. Initial value we know, which is 10 volts. So what is the final value? So in order to find the final value, we can use this voltage. So this voltage source will decide what will be the final value there. So first the capacitor voltage will discharge, and then it will be charged according to this voltage source. So in this case, we will also have to find out again what will be the voltage across the 3 ohms resistance if this connection is there. So we can again apply voltage divider rule, which is 6 plus 3 times 3, and this will give us the final voltage across, which is the final voltage across the capacitor. So when the steady state arrives, so that will be again 4 volts. In this case, it will be 4 volts. So Vf is 4 volts. So we have 4 plus 10 minus 4 e to the power minus t over Rc. Rc I didn't find yet. So Rc will be, when C is 2 farad, that's given. But what will be R? In order to find R, we have to find what is the resistance through which the capacitor will discharge. So that is, we have to make the source inactive, and we have to see what is the resistance the capacitor sees. And when we look that, we can see if we ignore the resistance here, ignore the voltage source here, this will be a short circuit. This will be replaced by a short circuit. So then the resistance that the capacitor sees is the parallel combination of 6 and 3. So 6 parallel 3 is 6 times 3, 18 divided by 6 plus 3, 9, so that's 2 ohms. So that is the value of the resistance. So Rc will be, R is 2 and C is 2, so that will be 4. So this one is 10 minus 4 is 6 e to the power minus t over 4. So this is the voltage, and we have to use this voltage to find the current across the capacitor, current through the capacitor. So that is C dV over dt. So we have to differentiate that. C is 2 and dV is this one. When we differentiate this one becomes 0, because that's the total voltage here. So this is total voltage final plus initial minus final, and then this multiplied by the exponential term. So when we differentiate this one, it will be 6 here times 6 times minus 1/4 e to the power minus t over 4. So that one becomes now minus 3 e to the power minus t over 4 amps. So that is the current. Now going back to the voltage, we could also use the other formula, which is the natural response plus the forced response. So the natural response is when we consider there is no source, that is the capacitor's discharging pattern. So that will become, the initial voltage is 10 e to the power minus t over 4, and the forced response will be the final value, which is 4, 1 minus e to the power minus t over 4. T over 4. So this is the forced response, which is the basically the charging pattern. When the source is there, it will reach the final value through this exponential term like this. So this is the forced response, which is when the source is present, and this is the natural response, which is the discharging pattern. So when we add these two terms, it becomes this one, it again becomes, if we look at this one, it becomes the same expression. So we can use one of these formula to find the voltage across the capacitor. That was V just. So whatever we designate that. So that's the voltage here. So we can use either of the two formulas. So one is this one, which is final value plus Vi minus Vf here, and then multiplied by the exponential term, or we can use the natural response, which is the discharging expression. When there is no source, basically the capacitor will discharge, and when we consider only the source with there is no charge like that, where there is no voltage stored in like that, so just the force term, we have this expression, and when we add those two, we get the total expression, which is as same as this one, which was found before.